Okay, so here is part 2 of the 1999 question number 3, which is a traditional standard kinetics problem. We just did part A on the previous video, and now we're on to part B, and this is the most involved part of the whole question. They want us to determine the order of the reaction with respect to each reactant. And what they mean by an order when they're talking about that is an order helps us gain some understanding of what the mechanism might be like. So if we know that a substance has an order, we know it's involved in the slowest step, also called the rate determining step of a mechanism. This problem we're going to use the data table, and we're going to investigate the order of bromine, and we'll investigate the order of nitrogen monoxide. So picking up where we left off, and hopefully you have a copy of the problem with you, we're going to start out by comparing the two trials. Now we have 3 trials total to look at. We're going to pick out 2 where one concentration stayed the same while the other concentration was changed. And so by comparing how the concentration of the second part changed, we'll be able to determine an order by looking at the change in the rate that we saw. We're going to start out here with experiments 1 and 2 as our comparison. Because nitrogen monoxide is held constant during the experiment and only bromine has been changed in terms of its initial concentration, we can see what effect the bromine had on the rate. So now I'm going to go ahead and put on the work that I had started before. Part A was listed up above, so here's my work for Part B. Now one way to do this is visually, and I'm going to bring the question back for just a moment. This doesn't always work, but sometimes it does. Here in the first example, in comparing experiments 1 and 2, I see that if you double the concentration of bromine initially, that doubles the initial rate. When we double a substance's concentration and the rate doubles, that's called first order. So we could immediately say that this is a first order reaction. We won't be able to do that though for determining the order of nitrogen monoxide because the numbers on the bromine concentration never match up perfectly. I'm going to go ahead and show you a mathematical way to do experiment 1 and 2 to determine the order of bromine, and then I'll do the same method to show you the order of nitrogen monoxide. So we're doing 2 separate calculations here. These calculations are based on the rate law, and you know that the general form of the rate law is rate equals K times concentration of the first reactant, which in this case is NO, then the concentration of the second reactant, in this case it's Br2. We're actually, to determine the order, we're going to find a ratio of rate laws. So we'll do the rate law for the first experiment and the rate law for the second experiment. Now taking a look at the numbers that are going to be involved, you can see that the numbers for the initial concentrations and rates are both higher in experiment 2 than experiment 1. So for making a ratio, it will be easier on us if we put experiment 2 in the top of our ratio and experiment 1 rate law will go in the bottom of our ratio. So we're going to put these numbers in now after we get the initial formula set up. So deciding that experiment 2 is going to be the top of the ratio, I'm going to put little subscript 2's here. These subscript 2's are not the traditional subscript 2 that goes into a formula. They're just going to show that this is experiment 2's rate law. Dividing that rate law, we'll also be comparing that then to experiment 1. So that's why all of these have little 1's down at the side. You can see that here's an equal sign happening twice, so this little part is going to go away. So rate 2 over rate 1 equals the rate constant times NO and Br from experiment 2 over NO and Br from experiment 1. Another factor that we're going to add into this are the orders. Orders are exponents, and the order for NO will be represented by the variable m, and it will be the same for this NO concentration and that NO. Orders do not change. The letter lowercase n will be the order symbol for the bromine. At this point, I'm going to use the data from the problem to substitute in everything that I know about this. So I'm going to substitute in rate 2, and the units for rate are molar or molarity per second. So there's my ratio of rates. K2 over K1 is unimportant to this work at all. We'll figure out K at the end. We don't need it right now. K will be the same thing for top and bottom. So because of that, it's going to be canceled out, because the same number over itself is 1. Now for the rest of this. The concentration of NO divided by the concentration of NO in experiment 2 is also the same. Do you see that it's also 1? We're going to go ahead and cancel it out. And that's going to leave us with our numbers for the bromine. So everything's set up now. One thing we can do, by the way, is to rewrite this, the concentrations in the order to the n. We can rewrite this as basically 0.024 over 0.012 all to the n, and that's an important part. Okay, so what do we have left? Well, if we carry this out, we have approximately 2. So the ratio of the rates is 2 to 1. The ratio of the initial concentrations here is also 2 to 1. And n is what we're solving for. So 2 equals 2 to what power? And n, the power that would make this work, is 1. So the order for, at this point, the order for this reaction in terms of bromine can fit into our equation is this. And at this point we still don't know what the order of NO is. So the order for bromine is first. And what this means in terms of the mechanism is that there's one bromine molecule involved in the slow step, the rate determining step, or perhaps even earlier, if that's the case. Okay, I'm ready to do the next part. So going back to our data, now I can compare two other experiments and determine the order for the nitrogen monoxide. What I'm looking for in the bromine column is two concentrations that are the same, where this is controlled and the NO is varied. Unfortunately, we don't have that in this setup, but we can still do the problem using what we just learned from our previous answer. So I'm just going to pick out two other two experiments. I could pick out 1 and 2. I could pick out, or sorry, I can't pick out 1 and 2. I could pick out 1 and 3 or 2 and 3, because in both of those experiments NO has been varied. So let's compare experiments 2 and 3. Now at this point, since I showed you one time, see if you can write the basic setup for the problem using the rate law ratio for experiments 2 and 3. And I can tell you right now, it's not going to matter which experiment you put in which place, above and below. So pause for a second, write that out, and then check your work. Okay, so here's the setup for my work. I'm going to do rate for experiment 2 equals K2 times NO concentration to the M times bromine concentration, and no longer is it N, it's now 1 because I know that from the previous experiment, or from the previous problem. Second, here in the bottom of the ratio, I'll do the third trial. And I need to fill in those, I forgot about those. And again, those little subscripts are just indicating what trial it is. It's not affecting any formulas or anything like that. So there's my setup. I'm going to go ahead and flip the page here because I'm running out of room. But I'm going to use all the data from experiments 2 and 3 to substitute in wherever I can. And I'm still going to cancel out K's. And so pause, fill in what you can, and then pick up with my work. Okay, so there's my work, and I'm going to put in some numbers now. So this is experiment 2's initial rate. Experiment 3's initial rate. So they're about the same. K2 over K3. K's are the same for these two. So long as temperature is not varied, K stays the same. We're going to get rid of those. That cancels out to 1. The concentration of NO initially in experiment 2 is 0.016. And that's to the M, we don't know yet. Below that we have experiment 3. The concentration was 0.032 to the M. Now for the bromine, we do know the order for this. And it's first order, so we plug that in. If you don't plug it in, you have two variables and you have a trickier situation. Okay, so we can do some work here now. I'm rewriting this. This number on the left side is approximately 1. On the other side we have 4. The 4 is the bromine part, 0.024 over 0.006. And then we can multiply that by 0.5 to the M power. Rearranging, I'm going to move 4 over to the other side by dividing, and now I get 0.25 because that's 1 over 4 equals 0.5 to the M. So now you should know what whole number you could plug in where we get 0.25 equals 0.25. M for this experiment would equal 2. What that means to us is that the reaction is second order with respect to the nitrogen monoxide. And so that means that 2 nitrogen monoxide molecules are involved in the step there. So I'm going to go ahead and stop at this point, and we'll pick up with part C, which is much shorter to do.